Remember the homework? So the two last homework assignments have had stresses that you've had to calculate from trusses. Do you notice that? You guys who have looked at the homework have probably noticed that. Let me do a truss problem today. I want to do it two different ways. I'm going to do it the way we did it in statics, and I'm going to do it the way that the people who didn't take statics with me did it, and you can see, you can each see the method that you did it, and the people who took statics from me can see an example of how you can do a simplified version of truss calculations, and the people who took it from someone else can see the approach that we used for every kind of structure. All right. So let's say we got this truss. Where these angles are 20 degrees. Each of these members is 1 meter long. There's a pin here, and there's a horizontal force of 5,000 newtons applied at the pin. And I'm going to number these members 1 and 2. In this case, there's 2 members, and they are both attached to pins. If there were 3 members, then one would be, you can think of it as like if one of those was a pin, that force would just squish this thing flat. You know what I mean? You know what I mean? If there was a 3rd member keeping it from getting squished flat, then one of those members would have to be a roller, or one of those joints. So the cross-sectional area we'll say is 0.001 meters squared, and we want to calculate the stress tensor, and then second we want to calculate a stress tensor that contains the maximum shear stress. The first thing we have to do is figure out the external loads on each member. And I'm going to do that 2 ways. I'm first going to do it with my approach, the way that we did all our structures in my statics class, and then I'm going to use the book approach for trusses.
Trust you that that's how it does it. Trust you?
You know, there's benefits and drawbacks for each of these. The approach that we used in statics works for everything. That's the main benefit of it. But the way that the book approaches trusses and frames, you have to split up the world into these 2 different categories. Then there's a bunch that don't fit into either category that the book didn't teach you how to do. But once you do that, splitting it up, if you have a structure that's in one of those 2 categories, you save a lot of equations and a lot of variables. So those are sort of the trade-offs. Okay, so let's start with my approach. So we'll do a free body diagram of member 1. This is a truss, which means that we can't include the weight. If we included the weight, these would not be in pure tension or compression. So we'll leave that off. Down here, there's a full force vector applied to the member by the pin. And over here, there are two forces. One is the force vector applied to member 1 by, okay, well, so in my approach, remember, this is one where we have to think about, we always included the pin with one of the members. And who remembers how we chose that? Yeah, we always included the pin at any joint with the lowest numbered member. So this is member 1, which means the pin we're assuming to be part of member 1. And so that means that, well, there's a force vector here that's the force on the pin by member 2. The pin is part of member 1, though, so that's the force on 1 by 2. And then also that 5,000 Newton force is applied to the pin. And since the pin is lumped in with member 1, we're including it here. I'll put the coordinate system on the ground right underneath that middle pin. And now I'll use the table. Pancake, artists, row, 4, marzipan. All right, so the coordinates of this point A are negative 0.940, 0. The about point, I'm also going to put at A for this member. In statics, you can put that anywhere. Subtract, and you get a row vector of zeros. Force vector of RAX, RAY. Cross product of 0. And then up at the top, the coordinates are 0, 0.342. The about point is negative 0.940, 0. Rho is P minus A, so that's positive 0.940, positive 0.342. The force vector is F12X, F12Y. And the cross product is 0.940 F12Y minus 0.342 F12X. And then the last one is the 5,000 Newton force. That's happening at the same place as F12, so we know that the row vector is going to be the same. You could go through those same steps, but you'd get this. The force vector is positive 5,000, 0. And the cross product is minus 0.342 times 5,000, which is 171. Negative 1,007. What am I doing wrong here?
That's right. 1710.
Okay. So then Newton's second law says RAX, RAY plus F12X, F12Y plus 5,000, 0 is equal to zeros. And the moment equation says 0.940 f12y minus 0.342 f12x minus 1710 is equal to 0. So our first three equations say RAX plus F12X is equal to negative 5,000. Our second equation says RAY plus F12Y is equal to 0. And our third equation says negative 0.342 F12X plus 0.940 F12Y is equal to positive 1710. And if you add up the variables that we have so far, you have F12 x and y components and RA x and y components. So that's 4 variables, 3 equations. So we're not done yet. We have to keep going. So we'll isolate the second member. Any questions about that first one? Yeah, in dynamics it can't. It has to be either a point that's fixed in an inertial coordinate system, like a pin joint connecting it to the wall or the floor or whatever, or the center of mass of the body. Only 2 possibilities. And if there's no fixed point, no pin joint or ball and socket joint or whatever, then it has to be the center of mass. Then you don't have any choice. In statics, everything is a fixed point, so. Okay, so free body diagram for member 2. At the contact, member 2 is, so what's touching member 2? Member 1, and what part of member 1? The pin, right? That pin is part of member 1. So you have this force on 2 by 1, which is equal to negative force on 1 by 2. And what about that 5,000 Newton force? That's not there because it's applied to the pin, and the pin is part of member 1. So that's all we have up at the top. And then down at the bottom, we have, I guess I'll call it RC. Is a tribute to Royal Crown Cola. I don't know. It should not be if quality is a... Okay, and then, so the table, pancake, artist, row, 4, marzipan. I'm going to keep the origin in the same spot, but I'm going to change the about point. I guess this time I'll move it over to RC, over to the point C. So this point, this force, negative F12, that's at the location 0.342. The about point is at 0.940. No, no reason to. I kept the same origin, but so I changed the about point from one spot to the other.
So the other conjoint?
Yeah. Subtract, and you get a row vector of negative 0.940, positive 0.342. The force vector is negative F12x, negative F12y. And the cross product is positive 0.940 F12y plus 0.342 F12x. And then at C, the coordinates are 0.940, 0. That's also the about point. So the row vector, you subtract and get 0. The force vector is RCX, RCY, and the cross product is 0. So Newton's second law says negative F12x, negative F12y, plus RCX, RCY is equal to zeros. And the moment equation says 0.940 F12y plus 0.342 F12x is equal to 0. And so we get equations 4, 5, and 6. 4 says negative F12x plus RCX is equal to 0. Equation 5 says negative F12y plus RCY is equal to 0. And the sixth equation says, I'll rearrange these, so 0.342 F12x plus 0.940 F12y is equal to 0. And we had 4 variables before, F12 and RA, and now we added RC. So we have 6 equations and 6 variables, and we can solve this. So let's do it. I'm going to write the augmented matrix. Okay, so we have 6 equations. Those are the rows. And the variables, I'll go F12x, F12y, RAX, RAY, RCX, and RCY. And then these are the constants. So can someone just read me the coefficients from equation 1? Do we have any F12x? 1. Y? RAX? RAY? RCX? And then constant? Okay. Equation 2, I'm guessing we have 0, 1, 0, 1. And then 0, 0. And then what's the constant? Okay. And then equation 3, what do we have?
Negative 0.342.
1, 2x? Okay. Okay. Maybe I can still see these. Okay, so equation 4 then, we have F12x, we have negative 1. RCX, we have positive 1. Constant is 0. Equation 5, f12y, we have negative 1. Our cy, we have positive 1, and everything else is 0. And then equation 6, f12x, we have 0.342. f12y, we have 0.940. And everything else is 0. And can a couple people solve that and keep solving it until 2 people get ones that match?
I got F12 to be negative 2500, 909.57.
Okay.
RA to negative 2500, negative 909.57.
Did you say negative 2,500?
Yeah.
Okay.
And then I got RC to negative.
Sorry, I missed the y one.
Oh, sorry. 909, negative 909.6 or 57.
Okay.
And then negative 2500 and 909.57.
Okay. Anyone else get that? All right, good. So what we get is on this one, we have negative 2,500, negative 909.57. You can use tangent to figure out the angle of that force. What do you think that angle is going to be? Yeah, right. That's just going to be directly in this direction with whatever the magnitude that is. What's the magnitude of this thing we keep getting? 2,500 and 909.57. $28.86. That's my guess. 2,660. Okay. And then this one, what about up at the top? Well, that's equal to, it's going to be an F12 plus 500 going going to the right in the positive x direction. That ends up being equal and opposite to this, so you get 2660 like that. So that's a weird coincidence, isn't it? That like we calculated these forces and they came out to be exactly equal and opposite to, they came out to be exactly equal and opposite and parallel to the member. That's crazy. But, you know, that's the two-force member thing. If you only have two forces, the member, if it's in equilibrium, that has to be the case. They have to be either facing each other or pointing away from each other and equal and opposite. That's the only way there can be equilibrium. And that's when we go to the truss calculation, the truss simplification after this, that's the basis of the simplification that makes these calculations so much faster. Okay, and then for the other one, let's see. At RC, we have this, 2660. And up here, we have negative F12, so that's positive 2,500, negative 909.57, which is this way. So any questions about that calculation? Why what? To get the angle? Yeah. I'm not doing anything. I'm just I just drew these, the force vectors that we calculated, I just drew them in the direction that we know. I mean, you can use tangent with those components to figure out that those forces are going directly in line with the members. That's all I was talking about.
Then we have to rotate it to get the internal lobes.
Mm-hmm.
The whole beam itself.
Right.
So I just don't remember doing it static.
Yeah, well, normally you would just use these as, you would just report these as force vectors. I just wanted to point out that those forces, since we have a two-force member, those forces have to be directly along the line of the member. And really all you have to figure out is whether the member is in compression with this amount or tension with this amount. Okay, so let's do the other approach, the truss simplification. And the idea of this simplification is we know for trusses that all members are just in pure tension or pure compression. Yes. And so we'll just assume the pins have tension applied to them by every member. If we end up with negatives at the end, then that just says they're in compression, not tension. And then so assume every member is just pulling on the pin like a cable would. And use Newton's second law on the pin. Or in this case, it's just going to be one pin we're going to have to do, but if you have complicated trusses, you use Newton's second law at a whole bunch of pins until your number of equations catch up with your number of variables. Okay, so free body diagram of the pin at the top. So there's the pin. What's acting on it? Well, we know that there's a force of 5,000 acting on it. And we'll say member 1 is pulling on it. Since it's a two-force member, we know the direction of that force. So I'll just call that F1. And member 2 is pulling on it. I'll call that F2. We know the direction of that force too. So Newton's second law says negative 0.940 F1, negative 0.342 F1. Plus positive 0.940 F2, negative 0.342 F2, plus 5,000 0 is equal to zeros. So you get two equations. The first one says negative 0.940 F1 plus positive 0.940 F2 is equal to negative 5,000. And the second one says negative 0.342 F1 minus 0.342 F2 is equal to 0. So you can write this system. There's equation 1, equation 2, F1 and F2, and the constant. So for F1 you have negative 0.94. For F2 you have positive 0.94. And the constant is negative 5,000. Equation 2, for F1 you have negative 0.342. For F2 you have negative 0.342. And the constant is 0. And so can you solve that one and let me know when you have answers? Hopefully we're going to get positive 2660 and negative 2660. Okay. So that says that member 1 is in tension of 2660. And member 2 is in compression of 2660. Okay, so it's considerably faster. The issue is just you have to deal with a lot of assumptions and stuff, and that's the tricky part about using these different methods. Is it's faster if you know that it applies, but you have to keep in mind what it requires for it to apply and whatnot. Okay, so now we're done with, we solved the truss, the two-way. They agree. That's good. So now how do you calculate the stress in those members? So for member 1, we'll think of it like this. With the positive x-axis along the long axis. And so then the XX stress is equal to, is it going to be a positive or negative stress? Or neither? Maybe imaginary. Positive because it's tension. Yep. So 2660 divided by the cross-sectional area is 2.66 times 10 to the 6th pascals. It's just in pure uniaxial tension, so the stress tensor is 2.66 times 10 to the 6th. And zeros. So how would we calculate? Well, first let's just calculate what's the max shear stress. That's what you usually need. So to calculate that, you'd take the maximum. Okay, let me step back for a sec. So we're skipping the whole step of calculating the principal stress tensor. Why is that? Yeah, it's already in the principal stress tensor. As long as there are no shear stresses, it's a principal stress tensor. So the maximum shear stress is 2.66 times 10 to the 6 minus the minimum divided by 2. So that's 1.33 times 10 to the 6 pascals. If we wanted to calculate a stress tensor that had that shear stress, how would we do that? Around which axis? Yep. Y or Z. Yep. So if we make Q equal to whoops, 0.7071, 0, negative 0.7071, 0, 1, 0, and then positive 0.7071, 0, positive 0.7071. We could do it about Z too. I did it about Y. Then the stress tensor with max shear is equal to Q times the principal stress tensor times Q transpose. Anybody have that in their calculator? Easy to, got that program in there? Nobody. Nobody. It's 18 people in the class, but nobody has done that. All right.
All those together?
What?
All those together?
Yeah.
Yeah.
Scroll up. In the four corners. Okay. 1.33 times 10 to the 6th, 0. 1.33 times 10 to the 6th, 0, 0, 0. 1.33 times 10 to the 6th, 0. 1.33 times 10 to the 6th. Yeah. And so the absolute value of the biggest shear stress you see is equal to that max shear stress that we got from that simple formula. Number 2 looks pretty much the same. This one's in compression. So the XX stress is equal to, what's the sign of this one? Negative, because it's in compression. So negative 2660 divided by 0.001. So this time we get negative 2.66 times 10 to the 6 pascals. And so the stress tensor, which is also a principal stress tensor, is negative 2.66 times 10 to the 6. Zeros everywhere else. The max shear stress is the maximum principal stress minus the minimum principal stress. Well, I guess you don't need absolute. No, don't actually. Yeah, that's important here. So not absolute value. It needs to be signed, and then divided by 2, and you get the same thing we got last time: 1.33 times 10 to the 6.
Why does it need to be signed? Because I mean, depending on how you shift it, couldn't you have negative or positive of the same shear?
It has to be signed when you put in the maximum and minimum. You know, because if you had, yeah, you know, like, it just has to.
Okay. I thought you meant no.
Right.
I was saying absolutely.
Yeah. And so if you do max minus min, you'll always get a positive answer for this. And then when you calculate the stress tensor with the maximum shear stress in it, that'll be positive or negative kind of at random. but the sign, the absolute value of it will be what you get from that formula. Okay, so for this one, you could rotate again about the y or z, and you'd get something similar. I'm not going through that humiliation again. Any questions about that? Yeah. All right. Well, I guess the next thing I want to do is I want to do an example problem where we do internal loads of a beam with all, where you have a torsion on it and point loads acting on it. I guess we'll have to do that next time, but that'll be sort of our entry into internal loads. Okay, that's it.